Hello everyone, my name is Pritesh Mishra and I am here to present our work called Falcon Live Reconfiguration for Stateful Stream Processing on the Edge. This work was done in collaboration with folks from University of Toronto, McGill University and Nokia Bell Labs. This work was presented at the ACM IEEE Symposium on Edge Computing conference where it won the Best Paper award. Starting off, I'll give a bit of background. What is stream processing? By definition, stream processing is a paradigm that processes data streams in real time as soon as they are generated, as opposed to, say, batch processing, where the processing is delayed until a huge amount of data is accumulated. The stream processing engine analyzes and organizes data events arriving and presents them for analysis to other applications as a continuous feed. Stream processing is quite popular nowadays, with most popular stream processing frameworks being Apache Flink, Apache Storm, Spark Streaming, and more recently frameworks like Nebula Stream, which grew out of research and is gaining momentum. These frameworks power business critical applications in many companies and enterprises around the globe. On this screen, we present a few notable industry use cases in production. Let's use a traffic monitoring application to describe some of the stream processing basics. The goal of this application is to control the traffic light based on the number of vehicles on a certain street. For this application, the data source is a motion activated camera that produces vehicle images when a vehicle passes in front of the camera. The camera images are called tuples. Operators in stream processing frameworks are processing units that process the stream and further produce another stream. So the first operator here is an aggregator that detects the number of vehicles in a car image and maintains a count of all cars seen so far. After the aggregator has processed the data, the current vehicle count is then sent to the next operator, which is then responsible for controlling the traffic lights, which is the consumer or commonly referred to as the SIC. Operators can either be stateless or they can be stateful. Typically, stateful operators hold on to some information in form of state that is then used for processing each data point. Processing of each tuple needs access to this state and also often gets updated with the processing of this tuple. In this example, the state stored by the aggregator operator is indexed by the camera ID attribute, which becomes the key, and the value is the vehicle count. The concept of key is crucial since it allows for effective scaling. If the number of cameras is huge, then the multiple instances of an operator can be created and each instance can be assigned a subset of keys, or in this case, cameras. One thing to remember though is that only a single instance of an operator can be allowed to process a key to maintain state correctness guarantees. Stream processing also supports windows where the tuples can be collected over a certain time interval and then can be released for processing. In this example, the images are collected in a time-based window of 2 seconds. This window is maintained at a key level granularity since it also becomes part of the operator state. So in this example, the window-based aggregator has two states, the count stored per key and the window maintained per key. So with these basics in mind, let's see how these stream processing applications are deployed. Traditionally, such applications are always deployed solely on the cloud. Continuing with our example, deploying this application on the cloud means cameras on each street stream their image tuples to the cloud data center where the images are processed. However, streaming data directly to the cloud incurs a high latency and has bandwidth bottlenecks. To avoid this, infrastructure providers offer a hierarchy of data centers organized in form of a tree. In this hierarchy, there are cloud data centers at the root or top of the hierarchy, with edge data centers being the leaves which are located closest to the data sources. Now, if the traffic seen by the cameras is low, then this data can be streamed to the cloud since the amount of data being transferred is also low. However, if the number of cameras increase for certain streets, Since this is a motion activated camera, this leads to more images being produced, which then consequently leads to a spike in the amount of data that is being transferred to the cloud. Since AGG operator effectively does a data reduction where the images are processed into vehicle counts, moving this operator closer to data sources would result in a significant reduction in data transfer cost. To do this, additional instances of AGG operator is created on the edge data centers, and the keys storing the data of these cameras in these areas are moved to these instances. So this reduces the amount of data that goes to the cloud. Note here that moving processing closer to the edge is beneficial only if there is sufficient user demand, because the edge resources are much more expensive as compared to cloud, and the reduction in network cost must offset this increase in compute cost. So, frequent fluctuations in user demand creates our first motivation for frequent reconfiguration, where the processing of the operators might need to be moved from the cloud to the edge or vice versa. Even if the application does not have variable user demand and the operators are always deployed on the edge, frequently moving data sources can also necessitate application reconfiguration. For instance, if I modify our original example to replace the static cameras with moving cars as the data sources, and the aggregator operator on street 1 holds and processes the data for cars C1, C2 and C3. Now, if the car C2 moves from street 1 to street 3, then the application needs to be reconfigured to move the processing and data of car C2 from AGG1 on street 1 to AGG3 on street 3. Hence, the second motivation of frequent reconfiguration is to support the mobility of data sources. So just to recap, there are two major motivations for systems to undergo frequent reconfiguration. First is to adapt to the frequent changes in user demand, and second is to adapt to frequently moving data sources. Existing solutions for application reconfiguration can be broadly classified in three varieties. The full restart approach stops the entire application, performs the reconfiguration, and then restarts the application. The partial pause approach stops only the affected operators and uses fine-grained transfer and on-demand fetch techniques to spread the impact of application disruption. Third, the hot backups approach replicates the state periodically to all possible locations where the reconfiguration could happen. Systems like Apache Flink and Storm follow the full restart approach, where the entire application is stopped, the state is moved, and then the application processing is resumed. This obviously incurs a huge downtime for application processing. In contrast, systems like Trist and Mises improve on this by only pausing the affected operators involved in the reconfiguration. Finally, the hot backups replicate the state to all locations where reconfiguration could occur, which is quite expensive. However, this still incurs downtime since it takes some time to transfer the state changes that happened between the last successful checkpoint and the trigger of reconfiguration. In summary, the existing solutions for reconfiguration are not well suited for low latency applications running on edge cloud. They either incur a significant downtime or they migrate the state inefficiently. None of these solutions support source mobility. Hence, we propose Falcon, a solution to enable seamless reconfiguration of application operators. This minimizes the application stoppage time during reconfiguration and provides support for mobility of data sources. Performing this reconfiguration is challenging, especially for a stateful operator. The first challenge is when a new operator instance is created or destroyed, connections between all operators of an application need to be recreated due to a global coordination mechanism. Second, the state transfer is a relatively long process depending on the size of the data and the latency network links. Third, while the state transfer is happening, the tuples modifying the state are also being processed. So maintaining state correctness is also challenging. And lastly, during the state transfer and the switching of traffic flow, the system needs to guarantee that tuples are processed in the exact order that they are arriving and are processed exactly once, which then means avoiding duplicate processing and ensuring fault tolerance. For the first challenge, Falcon avoids global coordination by proposing a novel late binding routing mechanism. For the second challenge, Falcon duplicates the tuple processing during reconfiguration, and the long state transfer time does not affect the application processing latency. Now, during the duplicate processing, the original source instance continues processing of tuples while the destination instance transfers the state. Tuple sent to the destination waits in a buffer. Once the state transfer is complete, the destination replaces the tuples stored in the buffer to synchronize the state. This maintains state correctness. Finally, using emit filters avoids duplicate processing, and our fault tolerance mechanism prevents tuples from getting dropped. Using markers allows us to maintain the strict processing order of tuples. I would encourage you to check the paper to understand the in-depth details of the reconfiguration protocol and its correctness mechanisms. Let us now visualize the reconfiguration protocol in action for a data source mobility scenario. Assume that there is a car C1 on street 1 connected to our framework. For each data source, Falcon provides a unified IP address that the system translates to the IP address of the nearest edge data center to connect to the data source. At the root, the system maintains a global node key mapping that indicates which key is assigned to which node for processing. Let's assume in this case, A1 instance is located on street 1 is assigned the key of C1. So the tuple 1 generated from car C1 gets processed at A1 and the state is reflected. Now, if the car moves from street 1 to street 2, A0 can process, if the car moves from street 1 to street 2, the car C1 is now disconnected from the street 1 edge and is connected to the street 2 edge. So the tuple 2 produced by the car cannot be locally processed by the edge, and as per our routing protocol, if something cannot be locally processed, then it will be forwarded to the parent. So tuple 2 is forwarded to the cloud. Now the instance on the cloud has a catch-all mechanism, so it can process tuples from any key. But before processing this tuple, the system checks if this key is already assigned to an operator instance. In this case, yes, C1 is already assigned to A1. Hence, a mobility scenario is detected. To handle this scenario, the system triggers a migration to move the state of the key C1 from A1 to A0. To do this, it first duplicates the processing of these tuples on both A0 and A1. So, tuples coming to A0 such as tuple 2 will be pushed down to A1. Now, while the destination A0 transfers the state from source A1 can continue to process the tuples and emit the results to the next operator. Once the state transfer is complete, A0 replaces the processing of tuple 2 but does not emit the results. This is the core idea behind Falcon's reconfiguration mechanism. After the migration of C1 from A1 to A0 is complete, tuples produced by the car, such as tuple 3, can be processed at the cloud at A0. The node key mapping has also now been reflected with the change in assignment. One important point to note here is we don't move the state from cloud to street 2 just because the car has connected to street 2. We have a mobility threshold where we wait for a certain time interval to see if the car does not move beyond this street. This is useful for situations where the car could be moving across multiple edges to a distant street, and this could lead to frequent expensive reconfiguration back and forth between cloud and multiple edges. In this example, let's assume that the threshold is not exceeded and the car continues to move to street 3. The car now produces a tuple 4 that reaches A3, but A3 is not assigned to process this key. So the tuple is forwarded to the cloud where it is processed and the state is reflected. Let's assume that the car stays on street 3 for some time and the wait threshold is exceeded. At this point, Falcon triggers another reconfiguration to move the processing from A0 to A3. In order to do that, the protocol remains the same. Tuple 5 is sent to both A3 and A0. Source instance A0 continues the processing of tuple 5 and emitting the result, whereas the state is being transferred by A3. Once the state transfer is complete, it processes tuple 5, the state gets reflected, but the result is not emitted. After the reconfiguration, tuple 6 produced by the car will be processed at A3. You can see that the assignment is also reflected. So this was an example of Falcon's reconfiguration protocol working in conjunction with its source mobility protocol to enable seamless mobility of data sources. I skipped some of the intricate details of markers used in the protocol to keep the example simple and easy to understand. But as they say, the devil is in the details. So I would encourage you to check the paper for the intricate details of the protocol, specifically how using markers in this protocol helps us to maintain the correctness guarantees. Evaluating the performance of Falcon in handling the mobility scenario, we have this graph where we measure the P99 latency over time. When the car moves from street 1 to street 2, there is a small spike of around 50 milliseconds latency during which the state is transferred from the cloud to the street 1 node. Then when the car moved from street 2 to street 3, there was another small spike of about 5 milliseconds for switching the connections. Finally, when the car stayed at street 3 for the threshold duration, there is another small spike of 40 milliseconds to move the state from the cloud to street 3. We will now compare Falcon's reconfiguration performance with existing systems. Recall that there are three varieties that we had discussed earlier. We chose the state-of-the-art system in each category: Flink for full restart, Mises for partial pause, and for hot backup. Since Rhino source code is not available, we implemented this system on top of Falcon and called it Falcon HB, where HB stands for hot backup. We considered two real-time applications for performance evaluation. We used the traffic monitoring application, which was used as a running example throughout the presentation, and a toll notification application from Linear Road Benchmark, which has a much larger state size and has a higher number of keys. The first metric we use for comparison is disruption duration. This is a period when the application latency is much larger than the standard latency. For Flink, obviously, the disruption duration is quite high, in the range of 14 to 19 seconds. This disruption is actually even higher in Mises, as it spreads the reconfiguration period over a longer time and fetches one key at a time. For Falcon HP, the disruption is much lower, as the state is already replicated at the new instance. In contrast, Falcon's reconfiguration protocol achieves orders of magnitude lower disruption as compared to the baselines. The second metric is peak latency jitter. This metric intuitively measures the height of the spike, whereas the previous one we were looking at the width of the spike. For this metric, we can see that Flink again has the highest peak because of the full restart approach. The peak latency of Mises though is much lower as it was able to spread the impact of reconfiguration over longer period. For Falcon HP, even with hot backups, we see that there is a spike of 500 to 2 seconds, 500 milliseconds to 2 seconds due to the time taken to transfer the state change since the last checkpoint. In contrast, Falcon achieves a latency of 42 milliseconds, which is about half the round trip time of the network latency. This again is orders of magnitude better than the other systems. In conclusion, Falcon proposes a novel key migration protocol to minimize the processing interruption during application reconfiguration. Using this, it is able to bring down the interruption to 40 to 45 milliseconds, which is 2 to 4 orders of magnitude better than the existing frameworks. While achieving this performance, Falcon also guarantees in order and exactly once processing and supports seamless mobility of data sources. We encourage you to check out the paper where there are many more interesting details about our system, including more baselines, application benchmark results, and more details about the protocol. Our system is also open sourced, so you can find the source code on GitHub. I hope you will give it a try. Thank you so much for listening, and please don't hesitate to reach out to us in case you have any questions or if you run into any issues while setting up our system. Thank you. Cheers.